For those of you who don't know me, I'm Drew, and I'm co-founder of Sonix. This is the agenda we'll cover today. I'll start off talking about something I think that's pretty obvious, and is, I guess, one of the driving reasons behind the development of the FD-SOI technology you've heard a couple talks about today, which is in building advanced digital SoCs, there are some very major power challenges. We'll then go through some general power management techniques, I expect most of which will be familiar to you, and then I'll explain how Sonix believes that the on-chip network actually has a substantial role to play in helping use those power management techniques. And then we'll talk a bit about some future work that we're looking at Sonix around how to take advantage of these capabilities into this phenomena that's been coined about dark silicon. So just a brief history of Sonix. Sonix is a 17-year-old company that pioneered the market for on-chip networks. I'll jump to the bottom. I'm very proud of the fact that our customers have delivered well over 2 billion ICs into the market based upon our chips. And that represents well over 200 design completions with a focus of delivering the right amount of function, but at a faster time to market and a higher quality level than what's readily available with most internal solutions. We do that by allowing people to really mix and match IP, which was the kind of fundamental idea back when this conference was founded many years ago now, is that we would not only be able to design IP cores, but we'd be able to use them very easily in such a fashion that the user of the IP core didn't have to understand in great detail how they worked. And to do that, Sonix introduced the idea of using networking techniques to isolate the cores from each other and from the fabric. And that allowed our customers to put together many chips very rapidly. We've always been focused on doing that with an eye towards the fact that the S in SoC stands for system, and we're attempting to enable our customers to map system concepts then into the chip using the on-chip network as the flexible component needed to adopt the appropriate communication architecture based upon the characteristics of the design. To do that, we need to deal with one of the largest challenges, which I've talked about in this conference before, of these large SoCs, which is the fact that the viability of the product is normally based upon how well they share key system resources, such as external memory. So memory scheduling is something that's an integral part of everything that we do. Today we'll talk more about the work we've been doing for about 10 years now on optimizing around power and to be as power aware as possible in what we're doing. Earlier this year, Sonix introduced an expansion of our business relationship with ARM. We have been a substantial collaborator with ARM for quite a while now. We've been a launch partner, if you will, as their highest-end CPUs have gone into application processors. We have been frequently the interconnect of choice that hooked up to them. And we've, of course, been supporting generations of AMBA starting back in 1997, I guess. And we fully support their initiatives such as the AMBA and all the way up through the most recent CHI, Trust Zone, and things like this. The recent announcement is relevant because it talks about not just continuing and enhancing our interoperability with ARM's standards and IP, but also some collaboration around power management. Last year in October, Sonix surveyed a wide swath of the industry, not just our customer base, asking them about what were their biggest challenges that they were encountering when implementing their SoCs, and specifically the on-chip network on the SoCs. And you'll see that there's a set of things here which are probably not surprising to you. The power, performance, and area trade-offs were, of course, very fundamental to implementing these designs, and that was pretty interesting. Another interesting point is that about half of the designs need more than a gigahertz at some places on the chip, particularly in the host processors. But of course, that means that about half still don't, so there's still a pretty broad range of implementation points. Maybe the most interesting one for this talk is the fact that The number and types of power domains is increasing rapidly. And so I'll blow up that graph where we can see that very few, less than half of the designs now have fewer than 5 power domains in them. And that means, of course, that half of them have more than 5 power domains. And so the challenge of how do we manage power on these designs is becoming increasingly interesting. Why? Well, obviously, power consumption is a huge concern. Everything in mobile has to run off a battery, and so we worry about how much energy it takes to get everything done, how much power we take in standby. It's a big selling feature. You've heard earlier things today about all the interesting applications in this Internet of Things, including a very hot topic of discussion this year has been wearable computers, both for personal use in the form of watches and glasses, but also e-health medical monitoring applications. In those devices, it's particularly interesting because the amount of volume left for a battery is much, much less than what we're used to having even in a mobile device, in a cell phone. So it's really important. I think in the wearable space, we have this very interesting phenomena today that we're being driven to higher levels of integration than we would normally expect, given the lack of maturity of the end applications, fundamentally because we have to fit into a form factor that defines a very small volume and a very low weight, and that means we can't afford many chips and we can't afford big batteries. But of course, it's not just in the mobile space. Things which plug into the wall also need to worry a lot about power. If you imagine a 28 nanometer design with billions of transistors on it, the leakage currents are frighteningly high. Power consumption in those devices always impacts the cost of the packaging and therefore the cost of the die. And of course, in many of the more consumer-oriented uses of line-powered devices, we have to worry about the various different energy standards, Energy Star and the like, which limits how much power we can draw, or even things which plug into the network and need to pull power off of technologies like Ethernet and power over Ethernet. And then when we get to the server rack, we have the constant challenge that people spend more money on cooling in many cases than they spend on the computers that they're cooling. So no new SoC development today can ignore power. So dark silicon is a phenomena that Mike Muller, the CTO of ARM, coined a couple years ago based upon the following observations. Because we can get so many transistors in our chips, we have this challenge that the amount of leakage associated with each of those transistors limits how many of them can be turned on at any moment in time. And there's things we do at the process level. We are introducing new processes to try to attack this, but we still use finer lithographies, and so the number of transistors still grows, and so the problem still gets bigger. Increasing the number of threshold voltages, adding dynamic voltage control, all those things help. But fundamentally, we have this requirement that some chunks, substantial chunks of the chips, are normally or frequently powered off. In other words, they're dark, and that's what the term dark silicon comes from. It's the imperative that you have to keep substantial chunks of your die powered off, even in its normal high efficiency modes of operation. Now, when it was described to the industry, it was described as a problem, as a challenge that we were all going to have to face. I'm here to say today that we believe it's an opportunity at Sonics to really rethink how we partition designs, how we repartition our SoCs to better exploit the performance while minimizing power and energy. So let's talk about some of the techniques that people use. So here from top to bottom are kind of the textbook things you can do at design level to do power management. 20 years ago, we were stopping clocks on dies to try to minimize the amount of active power that circuits were using by using clock gating, or actually stopping the entire clocks. The next thing was introduced in some cases were to realize that we may be in modes of operation that have lower frequency requirements, lower throughput requirements, and so we could slow down the clocks without turning them off. As leakage became a problem, we started switching power supplies off in local areas on the chip to try to eliminate leakage when that's the on-off voltage domains or power switching. And then as at the highest level of complexity is the situations in which we dynamically choose a voltage for the circuit that allows us to run the design at the frequency that we want. And generally, you choose the lowest voltage that allows you to run at that frequency and therefore try to save the most power. Now, there are IP-specific techniques. One that's worth highlighting is the big dot little approach that ARM's been promoting for the last couple of years, which is an architecture-level approach that says, run your software program on the IP that is best suited at this moment in time for what you need your software to be able to accomplish. Now, to implement these techniques, we have power managers on our chip. Often, they're done largely in software. So there are hardware registers that help us control the power state transitions of shutting down this clock or shutting off this voltage or retuning the operating point of this processor cluster. Of course, software-based solutions are always very flexible. Unfortunately, they tend to be pretty slow. Unfortunately, they tend to require the operation of a host processor who you might want to have shut off at the moment of time in which you're trying to make a power state transition to be on so the software can run. Some of the more advanced application processors for phones have implemented their power managers in hardware, where there's some parts of the fundamental control loops that are implemented in hardware. Obviously, they can be much more responsive. They can work with actual hardware signals that determine the state of things, and state machines do run faster normally in hardware. But of course, they're less flexible. And there's a number of interesting challenges that people have run into, including this phenomena of the power management deadlock, where in order to accomplish a power state transition at one domain, I need to do something through another domain which may also be powered off. And you can easily get into situations, and many SoCs have been designed that suffer from power management deadlocks, where you actually get into modes where you can't get powered back on without going through and resetting the system. So to reduce the clock power is maybe the simplest thing to talk about. Basic idea there is to reduce the clock frequency whenever you can, and to stop the clock when there's nothing useful to do. To get the best results we've found over our 17 years of doing this, that it needs to be architected into the IP. And at Sonics, we prefer a hierarchical approach, two-level approach. At the leaf level, our designers code clock gating down at the level of individual flip-flops. So at the level of registers or state machines, when there's nothing to do, we stop the clock. Basically, you take a look at the equation that determines whether or not a flip-flop, if clocked, would need a recirculate path around it, and you just don't clock it if there's no reason to recirculate. By doing this, we toggle only the input to the clock gating cell, which normally has a latch inside it. So you have one load on the clock instead of n loads, where n were the number of flip-flops that you saved. And so you save active power there. Then we gang these fine-level clock gates into a coarser level, which is at the level of an architectural unit in a design. So when we realize that if there is no activity in the larger circuit, we can easily gate off the clocks to the circuit. And if you do that well, then what you've saved isn't really flip-flop power, because we were already gating at the fine level. But what you do is you save the dissipation of the clock tree. And low-skew clock trees in these advanced process nodes tend to have a high capacitance associated with them. There's a lot of local buffering. And so by implementing this coarse grain well, you can save a lot of the clock power. We found that this approach allows very effective gating. Typical designs based upon Sonics achieve better than 99.5% of the flip-flops have a clock gate in the path. And many of the designs get better than 3 nines. For example, in one reference we had, there was a design that had 40,000 flip-flops in it, and only 16 of them were free running. And in fact, we know exactly where all 16 of them are. The reason they're not clock gated is because the overhead of putting a clock gate around them would introduce more clock power than what we would save. So that's how we reduce the clock-related power. Reducing the voltage-related power is similar in concept, but more difficult in implementation because there's state. that you lose. When you stop the clock, we don't normally lose state unless the thing we're stopping the clock to is a dynamic memory. When we remove the voltage, we typically are going to have some state we lose that we have to replace somehow or store in a retention cell or something. So to save the voltage-related power, we want to take away the power or reduce the power level, the voltage level, whenever possible. To do that, we partition the design into multiple power domains, and they're typically partitioned based upon both a logical understanding of the design, but also a physical understanding of how the design is going to be laid out, because the normal ASIC-style design approach has one supply voltage for each row of standard cells, and so you have to gang the cells together that you want to switch the power off to physically on the die. Now, reducing the voltage has been known for a long time to save big chunks of power. The active power equation for CMOS circuits is well known. It's proportional to the capacitance times the frequency times the voltage squared. So if you change the voltage term, you get a big savings because of the quadratic nature. And so we can do that. Even better, of course, is to switch off certain voltage islands within the design, because that takes our leakage to zero. So for circuits that are idle for some period of time, switching off the voltage makes a lot of sense. Of course, this is even more effective if you have modes of operation, as we see in many mobile devices, where large fractions of the chip are idle for most of the time, because then we can find more sections of the die which can be powered off. And those regions of the die really do go to near zero power dissipation. And I would argue that big dot littles from ARM is a pretty good example of that. In the normal use cases that people have for big dot little, you never have both processors on at the same time except during transitions. So we go from having a high degree of activity in the system, and so we're using our A15 cluster, which dissipates more power because it has a more aggressive circuit design. It also dissipates more power because it's just physically a lot larger. But when the application load goes down to a point, we can then transparently switch over to the A7 cluster, which doesn't have anywhere near as much performance, but is far more power efficient at lower frequencies than the A15. And of course, when the application fires back up, you can migrate backwards. So those are the general techniques. What role do on-chip networks play in this? Okay, so we've been talking about these power and clock domains. They are physically distributed around the chip, as the diagram I just showed you shows. And of course, the on-chip interconnect fabric has to connect to all of them. So the on-chip interconnect, somewhere in the path between these different blocks, has to deal with crossing these boundaries. How should we do it? Well, with standard fabrics, the natural choice is to create boundaries at the bus interface level. So here we see a set of components connected together. It's logically a bus here. The gray regions represent different power domains, and the red dotted line represents the power domain crossings. Okay. Now, if you take a look at this really quickly, it's obvious that the on-chip network itself ends up naturally being forced to be in a part of the chip that nobody likes, which is called the always-on domain. The always-on domain is the part that can never be switched off. And I think if you think about it pretty quickly for a little bit, you'll realize that with this type of an approach, this type of topology, the network has to be, such a network would have to be in the always-on domain. There's really no choice, because if anyone's alive and they have to talk to anybody else, the bus has to be there to talk to them. Turns out also that this is not a very nice place to partition the design from the perspective of doing the actual physical implementation, because the interfaces here tend to be some of the fattest, the largest wire count interfaces in the chip. An interface protocol like AXI, for a 64-bit interface has 300 odd signals in it for a single 64-bit interface. That's quite a lot of wires that would have to go across, for instance, an asynchronous boundary associated with crossing a power domain. Once we rethink the approach to building our on-chip network and we start to allow some more depth, some more hierarchy to show up in the topologies, we have some new choices that can make sense. Well, the equivalent of the bus approach is shown here, where we still are crossing the boundaries at the edges of the IP block, and the network is still stuck in an always-on domain. But that's really, as you see, not very effective, The first thing you recognize is the thin green blocks right next to the IP cores are the blocks we call the agents, and they provide the interface between the network and the interface sockets like XI that the IP cores are using. Well, if the IP core is powered off, there's really no reason to power up the agent, so we could at least move the boundary down here and begin to absorb that logic into the power domain of the IP core, assuming your logical and physical partitioning of the design works with that. But we can do better than that. If we realize that these two cores are actually controlled together, they're actually part of the same power domain, and so they will always be switched on and off together, well, then we can take a look at the connectivity and repartition the design to take advantage of that fact. And now we're crossing fewer times, and we're absorbing more of the network into the power domain so that they can be powered off. And you end up very quickly in a situation where the choice about what topology to use inside your network is impacted by where you want to draw the power domain boundaries of your chip. And so on-chip network fabrics like the ones that Sonics produce are optimized with a set of EDA tools so that we can allow our customers to readily change their topologies once they begin to discover what power management domains they are willing to pay for. But there's more to making something like this work than just figuring out where to cut the lines. Operating safely in a design that is aggressively power managed is a big challenge. I talked about power management deadlocks and things like this. There's a lot of work that goes into bringing up a platform based upon something that's aggressively power managed and splitting the, practically speaking, I mean, to many people, designers, splitting the network across those domains is a scary thing because how do I do this safely? So some technology that Sonics pioneered a while ago was to try to help with this by putting extra logic and features inside our networks. So if we take a look at our design, if we want to power down the target core down at the bottom right, there's handshake signals that go into our network that know about the different domain boundaries, and each of the initiator agents, not the initiators themselves, but the initiator agents, the little thin blocks up top, are told that this domain's going down, and they have the logic to flush all the paths that impact or intersect the domain that's in flight. So that allows us to make sure that before we actually shut down that domain, there's no transactions in flight to the domain. Then, if anyone tries to access a domain that's powered off, that stays local because the initiator agent knows that to get to this target, it has to cross a domain that's off. And so when he looks up the address to try to determine the route, he sees, hey, this is off. I'm going to go ahead and generate an error. That's because he knows the power state of each of the domains. So that's kind of interesting. That allows us to do the shutdown very safely and to deal with behaviors that aren't expected, like people talking to systems that are turned off on purpose. But what if we could do a design approach where we leave things turned off all the time and only wake them up when there's something for them to do? What role can the network play in helping determine, hey, there's something for you to do? Well, we have an analogy for that. The laptop here has an Ethernet port in it, and that Ethernet port almost certainly implements the wake on LAN protocol that's associated with Ethernet. So what does that mean? Well, that means that the computer can go into a sleep mode, and the network interface can cause the computer to wake up whenever packets show up that are intended for this computer. And we can do the same thing at the on-chip network level. So remember, the initiator agent knows the state of all the domains, and it knows the routing path from the request it's receiving to those domains. So I get a request. The initiator agent looks it up, finds out who does it go to, what's the state of the different components along the path. If that's off, he can go through this algorithm that we'll walk through here. So step One is he holds the transaction. Step two is he notifies the power manager, hey, here's a domain that you might want to wake up. And if the power manager is willing to wake it up because the mode the power manager is programmed into says that's a good idea to do, then he'll send the signals down. The target down in the bottom right will get powered up. Once the acknowledgement comes back through to the initiator, then the initiator can issue the traffic safely through the network. Okay? This is what we would call the auto-wake protocol approach. And it allows us to take a lot of the simpler blocks on the chip and put them into a normally off state where they can be turned on very quickly. In many cases, at a level of control that's below the knowledge of the device drivers. So if we have this kind of technology, what can we do with it? So let's look at an example. A lot of people talk about smartphone and tablet processors, so I thought that would be a comfortable image to use today. If we take a look at that at a block diagram at this level and we add some power domains in, the gray boxes here represent power domains, and some of them are single level. And if you look at the ones around the big dot little processor complex with the Mali core, those ones are hierarchical because we have a larger domain, which includes the coherent fabric and the DRAM controllers. And then, of course, we have smaller domains, which include each of the processors, or else big dot little doesn't work. On top of that, I'll overlay an image of our Sonics GN on-chip network and show how you can make partitioning choices that have the power domain boundaries at any arbitrary link boundary within the system. Okay, so SGN is unique in that it supports large numbers of domains. Of course, it does all the clock ending stuff I talked about before, but also has the hardware protocol support for doing on-off control there. Let's look at that in a little bit more detail. So you can have an unlimited number of domains, and they have different types. They can be on-off power switch. They can be dynamic voltage and frequency scaling, and you can have ones that just change frequency as well. At each of the places where one of our links crosses between domains, we automatically infer, or you can override and choose the appropriate style of link crossing to have. You can have a synchronous one, asynchronous crossing, or a mesosynchronous crossing if you have two clocks, or the same root clock, but the skew isn't well controlled between them. And then on top of that, we layer this power management interface for each one of the domains that we participate in. And so there's a two-wire handshake that allows the on-chip power manager to request and for us to acknowledge when it's safe to shut down a domain. But then we also have the auto-wake protocol that allows us to notify the power manager when it's a good time to wake up certain domains. If we put that all together with an appropriately designed on-chip power manager, you can have a complete solution for addressing the hardware power management needs of the chip, including an on-chip network, a power manager which will have both hardware and software components, and a tooling environment to help you make the partitioning choices so that you are building the right number of domains. By doing this, we can enable much finer grained power control. Why? Because we can shut things off more quickly, and we can wake them up so quickly that we don't even have to tell the drivers about it. Maybe the diagrams on the right will be helpful. Conventionally, if you want to shut off a block to save power, that's the green region on this time versus power graph, we have to wake up a CPU. He has to stack his registers so he can take an interrupt. We have to go find out who is the core. We have to service the interrupt basically to find out which core it is that wants to be shut off. Then we have to go do the work to actually get the system into a state where it's safe to shut him off. Usually that means going back to sleep for some time to wait for some timers to expire. And eventually, after having spent a fair amount of extra energy, we can go save some power. And then on the other side, it's exactly the reverse. We get woken up, say it's a good time to wake him up. I got to stack my registers again. Now I have to go through the sequencing to try to bring him back up. And so what limits the number of power domains, or the size of the power domains that software is willing to control, of course, is the ratio of how much power we can actually save versus how much energy it's going to take us to make those power state transitions. With solutions like this, we can save all the power shown below, where we can make most of these decisions in hardware without waking up a processor so that we can make them at much lower peak power. And we make them so much more quickly because, first of all, we don't have to do anything in software. And secondly, we don't have to wait. By using these hardware interfaces, we know completely and automatically when the different pieces have drained, when the pieces are done, so that we can get into the lower power state quicker. On the reverse, we can automatically come back up much more quickly as well. And of course, because we got turned on more quickly, in many situations we can get our work done faster too, and so we can even save power on the back end. Additionally, this style of approach allows us to reduce the loading on the general purpose operating system that's running on the host processor. And for those of you who probably have heard of this Android operating system, in a lot of these operating systems at this point, they don't service power management using interrupts anymore. They take the power management events and they bundle them into the OS timer ticks, which means the minimum granularity, the finest granularity you have around power control is now around 30 milliseconds. And so there's lots of power state transitions that don't make sense to do if you can't turn things back on for 30 milliseconds. And so by getting the CPU out of the business of some of this fine-grained control, there's some substantial power advantages. So we want to let you have as many power domains as you want with as fine a degree of control and with rapid and safe transitions. And so to summarize, we believe this technology is very powerful in helping people save enormous amounts of power. The combination of the appropriate on-chip network that can span the domains, the ability to be aware of the state of the domains, algorithms like our auto-wake algorithm for turning things on just in time to service the traffic and then shutting things off on the other side, integrated network capture and performance analysis tools. One thing that we've learned from working with a set of customers is the scenarios that you use for analyzing an SoC for power are very, very closely overlapped with the ones you analyze for performance. And so it's natural, as part of configuring the on-chip network, that you capture a fair amount about these operating and use case scenarios. And with a little bit of extra information captured, you can also estimate your power far better. With some automated support and a correct by construction approach, it appears these kind of technologies can help you save half of the power in your SoCs. Thank you very much for your attention.